Right. We're going to talk about cylindrical and spherical coordinates. This goes along with section 2.7 of the OpenStax textbook, Calculus Volume 3. Our main goal is to convert between the rectangular three-dimensional coordinates we've been using and then the cylindrical and spherical coordinates. So we'll start with cylindrical coordinates. The three coordinates are r, theta, and z. Now, z is the same z that you had with x, y, z, rectangular coordinates. And r and theta are the same r and theta from two-dimensional polar coordinates. So that should be helpful that if you know polar coordinates, then you know these three coordinates that you're switching and even the formulas we'll use to get between them. We see a general point here in three-dimensional space, of course, given by x, y, and z, but you can also get to it using r and theta, and that'll get to that spot in the xy plane, and then you go up with z in the same way. And there's a little link here to go to a GeoGebra interactive thing to play around with the cylindrical coordinates. And so you can drag this point around and see how the coordinates change in cylindrical coordinates. So feel free to interact with that. The formulas for converting, of course, z is equal to z, and then these are your polar coordinate formulas. X is r cosine theta, y is r sine theta. So if you had r theta z, you could use these to get x, y, and z. If you have x, y, and z, and you need to get r theta z, well, z is still the same, and we would use the Pythagorean theorem to get r, and then tangent to get theta. So let's say you were converting from rectangular coordinates 1, negative 3, 5 to the cylindrical coordinates. You would start by maybe saying z is still equal to 5, right? Because that doesn't change. But then to get r, you would use the square root of the sum of the squares of those first two components. And we always use the positive r for this because r is supposed to be a radius. So we'd use positive square root of 10 here. And then tangent of theta would be y over x. So that's negative 3 over 1, which is negative 3. And then the inverse tangent, and you want theta restricted to 0 over 2 pi. Again, with the calculator, sometimes this inverse tangent on your calculator will give you a negative angle. You want to convert that to the equivalent positive angle, coterminal positive angle. Again, z should be the same. There's an example converting rectangular to cylindrical. Now talk a little bit about spherical coordinates. Their rho, the Greek letter rho, it's not a P, it just looks kind of like a P. Greek letter rho, Greek letter theta, and Greek letter phi. So rho, theta, and phi, and theta is the same theta from cylindrical coordinates and polar coordinates. So that's the one thing you already know. Rho is pretty easy to understand. It's sort of a three-dimensional radius. So go straight from the origin to the point, and that shortest distance along that straight line, that's rho. So that should also be positive. And then phi is the azimuthal angle. So if you think of starting in the positive z direction and then drawing down towards the xy plane, that will give you your phi. Again, there's an interactive here so that you can mess around with changing this. In this one, you can change that there, and you change r. So some people do work with negative rho values. So this one does negative rho values, but we're going to try to use positive. And then you could see the effect of changing phi. So if phi hits pi over 2, you're at the xy plane. So phi only goes from 0 when it's at the positive z, and then it's pi or 180 when it's at the negative z. And then, of course, theta is the normal theta that just sweeps around 0 to 2 pi. Here's the equations that relate the two. We basically take the equations from cylindrical and replace r with rho sine phi. And that gives you your xy equations. And then z is rho cosine phi. And then you can actually see that from here because you can just draw a right triangle here. And this is also z, which, rho is the hypotenuse, So that's rho cosine phi, right, as the adjacent side. And then r, right, this is also r up here. That's rho sine. So just using that right triangle there with phi as your angle and rho as your hypotenuse, you can get the relationship between rho and phi and r and c. So that gives you these equations. Rho in terms of x, y, and z is just the three-dimensional distance equation. And then remember, theta is the same theta, so tangent of theta is still y over x. And then this one looks complicated, but it's really just inverting this equation. So solving for phi here, you'd have phi is inverse cosine of z over rho, and they've replaced rho with the square root of the sum of the squares from this one, so that you just use x, y, and z. But this is just inverse cosine of z over rho. If you want to go between cylindrical and spherical directly, you can, though most people just go to rectangular. It's kind of a middle step rather than remembering these, but you could if you remember those relationships there. All right, so say I had some rectangular coordinates here and I wanted to write them as spherical and cylindrical. I think we're just going to focus on spherical here. So rho is the easy one to get. It's just the square root of the sum of the squares. So square -1, square 1, square root of 6, and you get 8. And then the square root of 8 is 2 root 2. Theta is the same theta from before, and so it's inverse tangent of y over x. In this case, I get 3 pi over 4. And phi is inverse cosine of z over rho. We already have rho as 2 square root of 2. We already have z as square root of 6. So it's just square root of 6 over 2 square root of 2 is cosine of phi. Do the inverse cosine, and you get pi over 6. So there's your spherical coordinates. Now, if you're in rectangular coordinates and you say that x, y, or z is equal to a constant, you get the coordinate planes. We actually brought this up in section 2.2, I think. So it's interesting to look at when a single variable is equal to a constant for the other coordinate systems because it's not always a plane. So if we switch over to cylindrical coordinates, if we let r be equal to a constant, we get a right circular cylinder. If we let theta be equal to a constant, we get a half plane. So this extends infinitely in this direction, but not in the other, right? And because you're restricting to positive r values. And then if z is equal to a constant, that of course is the same because it's the same z from rectangular. Going to spherical coordinates, if rho is a constant, you get a sphere or spheroid. If you get theta as a constant, it's the same as cylindrical because it's the same theta. And if z is a constant, you get the top half of a elliptical cone, and specifically like a cylindrical cone. So that's phi being equal to a constant. Very cool. And of course, if phi was not acute, if it was, you know, between 90 and 180, some obtuse angle, it would be a cone down here. All right, so what if I look at this shape and I want to know what the equation is in terms of some other coordinate systems? We looked at these quadric surfaces with rectangular coordinates, but what about using maybe cylindrical or spherical? So the correct answer here is C, that z is equal to r. If z is equal to r, then you do get the elliptical cone, specifically the right circular cone we had as a quadric surface, and it's a much simpler equation than the rectangular coordinate equation. You notice that this line that kind of forms the outside of it is just the line. It's like y equals x, but in this case, it's z equals r. And then you let theta be a free variable, so theta can circle around, and you get the full shape of that cone. So this is using cylindrical coordinates to get that quadric surface. Here, try another one. So this is obviously a sphere centered at the origin. We're not told the radius of this, but you should still be able to figure it out. And you should have gotten answer choice C, because we did talk about when the rho is equal to a constant that you get a sphere. In this case, it looks like the radius of the sphere is 6. So using spherical coordinates, you can get a much simpler equation for the equation of a sphere. And that's it for this presentation by Matthew Watts, containing images and text from the OpenStax textbook Calculus Volume 3 by Jed Herman and G. Strange, CC by NCSA. Thanks for watching, and on to Chapter 3.